What's up, everyone? Interstellar Sleep here with another deep dive that's definitely going to make you think. You know, when you watch Christopher Nolan's Interstellar, you're hit right in the gut with that feeling that time is running out. The blight is consuming the crops, the oxygen is thinning, and dust is covering everything. But what if our greatest enemy didn't come from the ground, but from that giant star that keeps us alive? An invisible monster living 150 million kilometers away. Solar and geomagnetic storms. And listen, if you think Tars had his work cut out for him fixing the Endurance's systems amidst a giant tidal wave on Miller's planet, imagine what one of these storms would do to your Wi-Fi, your phone's GPS, and the entire planet's electrical grid. Here's the deal. The sun isn't just a static ball of fire. It's a chaotic nuclear reactor. Every 11 years or so, it enters a period of maximum fussiness. It starts spewing charged particles and radiation everywhere. Imagine the sun sneezed, but that sneeze travels at millions of kilometers per hour toward Earth. When those particles hit our magnetic field, which is like the invisible shield of our spaceship Earth, things get intense. On one hand, we get the auroras, which are beautiful, like a cosmic light show. On the other hand, we get technological chaos. In Interstellar, Cooper has a line that sums up our channel pretty well. We used to look up at the sky and wonder about our place in the stars. Now we just look down and worry about our place in the dirt. Solar storms are the real-life version of that fragility. In the movie, humanity has to leave Earth because the environment became hostile. A large-scale solar storm, one of those that happens once every 500 years, could literally fry our modern civilization in minutes. There wouldn't be dust, but total darkness. No internet, no power, no communications. It would be the perfect Nolan movie plot, but the problem is scientists are warning us it's a matter of when, not if. To understand the danger, we need to go back in time, specifically to September 1st, 1859. There was an amateur astronomer named Richard Carrington. He was observing the sun when he saw two intense white flashes erupting from a sunspot. It was the first time anyone ever recorded a solar flare. Less than 18 hours later, Earth's shield was hit. The result? The Carrington event. The auroras were so bright that people in the Caribbean could read the newspaper at night. But the dark side was that the telegraph system, the internet of the time, went haywire. Operators got shocked, telegraph paper caught fire, and machines operated on their own, even when disconnected from the battery. If that happened today with our total dependence on satellites and microchips, the damage would be in the trillions of dollars. It would be as if Gargantua were sucking in not light, but our entire digital infrastructure. You can't talk about the sun without mentioning Eugene Parker. This guy was a genius. In the 1950s, he proposed the existence of the solar wind. Back then, everyone thought he was crazy, but he was right. So right that NASA launched the Parker Solar Probe, the first spacecraft to touch the sun, flying through our star's outer atmosphere to understand these cycles. Another heavy hitter is Hannes Alfvén, the father of magnetohydrodynamics, a fancy name for the science of how plasma and magnetic fields interact. Thanks to scholars like them, we now have the Space Weather Prediction Center, SWPC, which is like our real-life NASA control room, monitoring the sun 24/7 to warn us if the solar sneeze is coming our way. Movies and music have always been fascinated by this solar apocalypse. Remember the movie Knowing with Nicolas Cage? The ending is basically a game-over level solar storm that wipes everything out. It's a bit exaggerated, of course, but it taps into that primordial fear we have that the sun, our creator, could become our destroyer. In music, bands like Muse love these space themes. In Supermassive Black Hole or Neutron Star Collision, they capture that chaotic energy of space. Even Coldplay with the album Music of the Spheres tries to translate that cosmic vibe. And in real life today, we have Elon Musk. In 2022, Starlink lost about 40 satellites at once due to a mild geomagnetic storm. That shows that even with the most modern tech of 2025/2026, we're still as vulnerable as Cooper trying to dock a spinning ship. We are now entering, between 2024 and 2026, what scientists call the solar maximum. It's the peak of the 11-year cycle roller coaster. This means the chances of seeing auroras in unusual places, like we recently saw at lower latitudes, are huge. But it also means power grid operators and satellite companies are on high alert. Imagine the economic impact. If large-scale transformers blow, it would take months to manufacture new ones. We'd be months without power. No power, no pumped water, no water, and we're right back to Interstellar's resource crisis. Going back to the idea that love transcends dimensions, maybe our greatest defense against these global events is human collaboration. Just like in the movie where sacrifice and science go hand in hand to save the species, understanding the sun is our way of building a protective tesseract. We study these storms not to live in fear, but to be ready, so that when the sun roars, our technology is resilient enough to keep the lights on and human connections alive. Solar storms remind us we're just passengers on a blue rock traveling through the void, and, as Old Man Brand would say, do not go gentle into that good night. We should rage against the ignorance and use science to light the way, even when the sun tries to switch us off. If you've seen Christopher Nolan's Interstellar, and let's be real, if you're here, you probably have it on repeat like I do, there's one scene that literally defines the word anxiety. You know the one. Cooper, Brand, and Doyle land on Miller's planet. They're looking for a signal, but then they see those mountains in the distance. Except Doyle realizes too late. Those aren't mountains, they're waves. That scene is a terrifying, high-stakes look at what happens when gravity goes into overdrive. On Miller's planet, the massive gravity from the black hole Gargantua creates tides that are miles high. But back here on Earth, we have our own version of that cosmic dance. It's a lot quieter, but it's just as powerful. It's the relationship between us and that glowing white rock in the sky, the moon. Now, we're talking about lunar influence and tides. We're going to look at how the moon is literally pulling our oceans toward it, why coastal cities like Los Angeles and places in Spain are currently underwater, and how the moon's wobble is a real thing that's making our lives a lot more complicated. Let's start with the basics. Why does the ocean move at all? It's basically a giant game of tug-of-war. Isaac Newton, the guy who basically wrote the rule book for the universe back in 1687 with his Principia, was the first to really nail down that gravity is what's doing the heavy lifting here. The moon's gravity pulls on Earth's water, creating a bulge on the side facing the moon, but because of centrifugal force, the Earth spinning like a top, there's another bulge on the opposite side. That's why we usually get 2 high tides a day. It's like the Earth is breathing in and out, controlled by a rhythmic celestial metronome. But it's not always a steady beat. We have things called spring tides and neap tides. When the sun, moon, and Earth all line up during a full moon or new moon, their gravity combines into a superpull. This is when tides get extra high. In the science world, we call this syzygy. It sounds like a cool indie band name, but it's actually a recipe for coastal chaos. In Interstellar, Nolan used the concept of tidal locking and extreme gravitational pull to show how time and environment are linked. On Miller's planet, every hour is 7 years back on Earth. The gravity is so intense it literally warps the fabric of time. Now the moon doesn't warp time for us, thankfully, or I'd be late for everything, but it does warp our geography. Scientists like Kip Thorne, the Nobel Prize winner who was the science advisor for Interstellar, helped Nolan visualize how a black hole would pull on a planet. Our moon does a light version of this. It doesn't create miles-high waves, but it does create king tides. And in 2025, these king tides are becoming a major character in our own survival story. Long before we had satellites, people were obsessed with the moon. Johannes Kepler, the guy who figured out how planets orbit, actually suggested the moon caused the tides back in the early 1600s. People thought he was crazy. Even the great Galileo Galilei mocked him for it, thinking the idea of a distant rock pulling on our water was occult nonsense. It wasn't until Newton came along and gave us the math that we realized Kepler was right. Later in the 1700s, a French genius named Pierre-Simon Laplace took it further. He realized that the tides aren't just about gravity, they're about how water moves in basins, affected by the Earth's rotation, the Coriolis effect. He turned tidal theory into a complex fluid dynamics problem. These guys were essentially the Cooper and Tars of the Enlightenment, trying to solve the equation that explains our world. Fast forward to today. We aren't just looking at the moon through telescopes anymore. We're feeling its pull in our living rooms. If you've checked the news lately, Los Angeles has been getting hammered by nuisance flooding. It sounds polite, but it's anything but. High tides are pushing seawater into the streets of Malibu and Santa Monica, even on sunny days. And look at Spain. Recently, we've seen devastating floods in regions like Valencia. While the main cause was a DANA, a high-altitude isolated depression, the sea level and tidal cycles play a huge role. When the ocean is high due to a lunar cycle, the rainwater has nowhere to go. The drains can't empty into the sea because the sea is pushing back. It's a bottleneck effect that turns a bad storm into a historic disaster. The scary part? The moon has a wobble. It's an 18.6-year cycle in its orbit. For half of that cycle, it actually suppresses tides, making sea level rise look slower than it is. But in the other half, which we are entering soon, it amplifies the tides. Combine a wobbling moon with the rising sea levels from climate change, and you have a recipe for what NASA calls a surge in coastal flooding in the mid-2030s. We're basically heading toward our own Miller's Planet moment where the water won't stop coming. The moon isn't just a scientific object, it's a vibe. From Frank Sinatra wanting to fly me to the moon to Nick Drake's haunting Pink Moon, we've always seen it as something romantic or mystical. But in contemporary culture, that vibe is shifting toward the eerie. Think about the movie Deep Impact or even the disaster flick Moonfall. We're starting to see the moon as a potential threat. Even in music, artists like Radiohead or Coldplay with Music of the Spheres often use space and planetary alignment as metaphors for things being out of our control. When Jay-Z launched his streaming service Tidal, the name itself suggests a powerful, unstoppable force. We use the word tidal to describe everything from waves of emotion to political shifts. It's because deep down we know the tides are one of the few things humans haven't been able to conquer. We can't stop the moon from pulling. Right now, scientists at NOAA, the National Oceanic and Atmospheric Administration, and NASA are using radar altimetry from satellites like the Sentinel-6 Michael Freelish to measure the height of the ocean down to the centimeter. They're finding that the moon's wobble is going to make the 2013s a decade of tidal record breaking. There's also fascinating research into paleotides. Geologists are looking at ancient rock formations to see how the moon affected the Earth millions of years ago when it was actually closer to us. Did you know the moon is slowly drifting away from us at about 1.5 inches a year? Billions of years ago, the tides would have been absolutely massive, real-life interstellar levels of crazy. In the end, it all comes back to that one core theme from Nolan's movie, gravity and love. They're the two things that transcend time and space. Gravity is what keeps the moon in orbit. Gravity is what moves the tides. It's a constant, invisible bond. But as the moon pulls the water higher and threatens our coastal homes, we have to use that other force, love, to take care of each other. Love for our planet, love for our future generations, and the drive to use science to protect them. We're at a point in history where we can't just ignore the blight or the rising water. We have to be the Coopers of our time, using every bit of data, every historical lesson from Newton to Thorne, to build a world that can withstand the pull. The moon is a reminder that we are part of a much bigger machine. Every time you see a high tide or a beautiful aurora, remember, you're watching the universe work. It's beautiful, it's a little scary, but it's home. Think back to that feeling you get when you're watching the first act of Interstellar. The dust is everywhere. It's in the food, it's in the lungs, it's in the future. There's this heavy, looming sense that the Earth has decided it doesn't want us anymore. Cooper says it best. We're not meant to save the world, we're meant to leave it. But while the movie focuses on a biological blight that's choking the planet, There's another threat that's been drifting through the cold, dark silence of space for billions of years. It doesn't care about our politics, our crops, or our dreams. It's the ultimate reset button for life on Earth, asteroids and comets. Now we're looking at these cosmic bullets, the history of how they've shaped our world, the heroes working to stop them, and why, just like in Interstellar, our survival might depend on us looking up before it's too late. Before we get into the world-ending stuff, let's clear up the terminology. Asteroids are basically the leftover scraps from when the solar system was built about 4.6 billion years ago. They're mostly rock and metal, hanging out in the asteroid belt between Mars and Jupiter. Think of them as the construction debris of our cosmic neighborhood. Comets, on the other hand, are what the late great astronomer Fred Whipple called dirty snowballs. They're made of ice, dust, and frozen gases. When they get close to the sun, they start to melt and outgas, creating that iconic glowing tail. The scary part isn't what they're made of, it's their kinetic energy. These things travel at tens of thousands of miles per hour. When something that big hits something as solid as Earth at that speed, the energy release is equivalent to thousands of nuclear bombs going off at once. For a long time, we didn't really think asteroids were a big deal for Earth's history. That changed in 1980 thanks to a father-son duo, Luis and Walter Alvarez. Walter was a geologist looking at layers of clay in Italy, and he found something weird, a thin layer of iridium that dated back exactly 66 million years. Iridium is super rare on Earth's surface, but very common in asteroids. This was the smoking gun for the Chicxulub impact. They proposed that a 6-mile-wide rock slammed into the Yucatan Peninsula in Mexico. It didn't just kill the dinosaurs with the blast, it kicked up so much dust, sound familiar, Interstellar fans, that it blocked out the sun for years. No sun means no plants means no food means, well, goodbye, T-Rex. This research fundamentally changed how we see our place in the universe. We aren't in a safe bubble, we're in a cosmic shooting gallery. In Interstellar, the enemy is invisible and slow. In an asteroid scenario, the enemy is visible but incredibly fast. But the theme is identical: humanity's resilience. When Brand says, "We must reach far beyond our own lifespans," she's talking about the survival of the species. An asteroid impact is the only natural disaster we have the technology to actually prevent. We can't stop a volcano, we can't stop an earthquake, but we can move a rock. Nolan's film is about the Plan B, finding a new home. But scientists today are working on Plan A, making sure we don't have to leave Earth in the first place. We used to think these impacts only happened every few million years. Then came February 15th, 2013. Over the city of Chelyabinsk, Russia, a meteor about 60 feet wide exploded in the atmosphere. It wasn't even a large one by cosmic standards, but the shockwave blew out windows for miles and injured over 1,000 people. It was a massive wake-up call for the world. It showed us that smaller collisions can cause massive tsunamis if they hit the ocean, or devastating forest fires if they hit land. Before that, we had the Tunguska event in 1908, an explosion that leveled 80 million trees in Siberia. If that had happened over London or New York, those cities would have been wiped off the map. If you grew up in the late 90s, you remember the great asteroid movie war of 1998. You had Armageddon, Bruce Willis, explosions, and Aerosmith, and Deep Impact, a bit more science-y and emotional. Armageddon is a blast, but it's basically cowboys in space. Deep Impact actually got a lot right about the tsunami and the dust consequences. Then in 2021, we got Don't Look Up. This movie was a biting satire on how we handle or don't handle scientific warnings. It used a comet as a metaphor for climate change, but it also highlighted the frustration of scientists who see a planetary killer coming while everyone else is distracted by social media. It's a darker take on the interstellar mission. What happens when we don't listen to the Coopers and the Brands of the world? We aren't just sitting ducks anymore. In 2022, NASA pulled off one of the coolest interstellar-style missions in history, DART, Double Asteroid Redirection Test. They intentionally crashed a spacecraft into a small asteroid called Dimorphos just to see if they could nudge it out of its orbit. And guess what? It worked. We proved that we can actually deflect a threat. We're basically building a tesserado of protection around our planet. Scientists like Dr. Amy Mainzer, who inspired Don't Look Up, and organizations like the B612 Foundation are working every day to map every near-Earth object, NEO. They use things like the Torino scale to rate the risk of an impact. Right now, there are no planetary killers on a collision course, but we're finding new, smaller rocks every single day. At the end of the day, why do we care so much about these rocks? Why spend billions of dollars tracking dust in the dark? It goes back to what we always talk about here on this channel: love. In Interstellar, love is the data. It's the signal that helps Cooper save Murph. In our world, the data is the science we use to track asteroids. Our desire to protect our children, our homes, and the beauty of this blue planet is what drives the survival instinct Dr. Mann talked about. Saving the world from an asteroid isn't just about physics. It's the ultimate act of love for every human being who has ever lived and everyone who hasn't been born yet. It's our way of saying, not today, universe, we're staying right here. So next time you look up at the night sky, don't just see cold, distant points of light. See a world worth protecting. See a future that we are actively building. In Christopher Nolan's Interstellar, space is represented as this vast, silent, and intimidatingly clean frontier. When the Endurance slips through the silence of the void, it's just them and the stars. But back on Earth, the world is a mess, covered in the blight and choking on dust. Now imagine if that mess didn't stay on the ground. Imagine if we took all our dust, all our broken dreams, and all our discarded technology and threw it into the one place that's supposed to be our escape hatch. Now we're talking about space junk, orbital debris. It's the blight of the heavens, a growing ring of trash that could literally lock us on this planet forever. We're going to look at the Kessler syndrome, the explosion of commercial space travel with giants like SpaceX and Blue Origin, and why our littering problem might mean we never get to see Gargantua for ourselves. When we think of space, we think of nothingness, but the orbit around Earth is actually getting pretty crowded. Right now, there are millions of pieces of man-made debris orbiting our planet. We're talking about dead satellites that ran out of juice decades ago, spent rocket stages, and even tiny flecks of paint. Now you might think, it's just a paint fleck, who cares? But remember the physics. These things are traveling at 17,500 miles per hour. At that speed, a tiny piece of metal the size of a marble hits with the force of a bowling ball going 300 miles per hour. It doesn't just hit a satellite, it shatters it into 1,000 more pieces. To understand the history of this problem, we have to talk about a man named Donald J. Kessler. Back in 1978, while working for NASA, he proposed a terrifying theory that we now call the Kessler syndrome. Kessler's idea was simple but chilling. As the density of objects in low Earth orbit, LEO, increases, a single collision between two objects could create a cloud of debris. That debris then hits other satellites, creating more debris. It's a chain reaction, a cosmic domino effect. If this goes far enough, the entire orbit becomes a no-go zone. We wouldn't be able to launch GPS, weather satellites, or even the Endurance itself. We would be trapped under a cage of our own garbage. It's the ultimate irony. The very technology we use to reach for the stars could be the thing that keeps us from ever touching them again. In Interstellar, the mission is to leave a dying Earth. But think about the launch scene. The Ranger breaks through the atmosphere and leaves the dust of Earth behind. But what if the dust was actually in orbit? If the Kessler syndrome had been in full effect in Cooper's world, they never would have made it to Saturn. The Ranger would have been shredded by a cloud of old 1990s satellite fragments before they even left the atmosphere. Nolan's film is about looking up and moving forward, but space junk is about the weight of our past. It's the physical manifestation of our use and discard culture. If we want to be explorers like Cooper, we have to stop being tenants who don't clean up after themselves. This brings us to 2026, the era of commercial space travel. We are currently living through a revolution. SpaceX, Elon Musk. They've changed the game with reusable rockets, the Falcon 9, but they've also launched Starlink, a mega constellation of thousands of satellites designed to bring internet to the whole world. While the goal is noble, it's adding a lot of traffic to the orbit. Blue Origin, Jeff Bezos. With their New Shepard and upcoming New Glenn, they're aiming to put millions of people living and working in space. Virgin Galactic, Richard Branson. They're making suborbital space tourism a reality for the ultra-wealthy. The balance. On one hand, these companies are making space more accessible, bringing us closer to the interstellar future. On the other hand, more launches mean more risk. SpaceX has been proactive, giving their satellites automated collision avoidance and the ability to deorbit themselves at the end of their lives. But as more countries and companies join the race, the rules of the road are getting blurry. We're in a space gold rush, and history shows that when people rush for gold, they usually leave a lot of trash behind. If you want a visual of the Kessler syndrome, you don't even have to use your imagination. Just watch the movie Gravity, 2013. That whole movie is basically a Kessler syndrome, the movie. Sandra Bullock's entire ordeal starts because a Russian satellite is blown up, triggering a chain reaction that wipes out the space shuttle and the ISS. It's a terrifying, visceral look at how junk can turn space into a graveyard in minutes. And then there's Pixar's WALL-E. Remember the scene where the ship leaves Earth? It has to punch through a literal shell of satellites and garbage surrounding the planet. It's a funny moment that's actually a pretty grim prophecy. In music, artists like David Bowie or even Radiohead often sing about the static and the noise of modern life. Space junk is just the physical version of that static, the background noise of our civilization cluttering up the silence of the spheres. The good news? We aren't just sitting around waiting for the dominoes to fall. Scientists and startups are getting creative. ClearSpace One, a European mission designed to use a giant claw to grab pieces of junk and pull them down to burn up in the atmosphere. Astroscale, a Japanese company working on magnetic docking to retrieve dead satellites. Laser Broom. Yes, scientists have actually researched using ground-based lasers to nudge debris into lower orbits so it burns up. We're seeing a shift in research towards sustainable space. Just like we're trying to clean up our oceans, we're realizing that the orbital environment is a natural resource that we need to protect. We always come back to the same theme here at Interstellar Sleep: love. Brand says love is the one thing that transcends dimensions. If we love our future, if we love the MRFs who are going to be born 50 years from now, we have to care about the trash we leave behind today. Space shouldn't be a graveyard of 20th century tech. It should be a clean, open window to the rest of the universe. Every time a company like SpaceX successfully lands a rocket or deorbits a satellite, they're showing a form of stewardship for the future. We are the bridge between the people who first looked at the moon and the people who will eventually walk on planets in other galaxies. Let's make sure that bridge isn't blocked by a cloud of scrap metal. Let's keep the path to the stars clear. When we watch Interstellar, we're mostly focused on the big, obvious dangers. We're worried about the massive waves on Miller's planet, the frozen clouds on Man's planet, or the crushing gravity of Gargantua. But there's a silent, invisible killer that Cooper and the crew are fighting every single second they are outside of Earth's atmosphere. It's not something you can see, smell, or feel until it's too late. Now we're talking about cosmic radiation. It's the invisible rain of the universe. We're going to explore how these high-energy particles shape the history of science, how they affect our lives here on the ground, and why protecting ourselves from them is the biggest hurdle for us to ever become a truly spacefaring species. Imagine the universe isn't empty. Imagine it's a stormy ocean, and instead of water, it's filled with subatomic particles, protons and atomic nuclei, traveling at nearly the speed of light. That is cosmic radiation. There are two main flavors of this space weather: galactic cosmic rays, GCRs. These come from outside our solar system, likely from massive supernova explosions far across the Milky Way. They are the heavy hitters, super high energy and very hard to shield against. Solar particle events, SPES. These come directly from our sun. During solar flares, the sun spits out a stream of protons that can hit a spacecraft like a radioactive sandstorm. Here on Earth, we have two layers of protection: our magnetosphere, a magnetic shield, and our atmosphere, a physical shield. It's like the Earth is giving us a permanent protective hug. But the moment you leave that hug, like the crew of the Endurance, you're exposed to the raw power of the stars. The history of this discovery is actually pretty wild. Back in the early 1900s, scientists noticed that something was ionizing the air, even in lead-shielded containers. Most thought it was coming from rocks in the ground. Then came Victor Hess in 1912. This guy had some serious Cooper energy. He took a series of daring balloon flights going up to 17,000 feet without supplemental oxygen. He found that the higher he went, the stronger the radiation got. He proved that this radiation wasn't coming from the Earth, it was coming from above. He literally discovered cosmic rays while gasping for air in a wicker basket in the sky. He won the Nobel Prize in 1936 for that discovery. Later, Robert Millikan, another legendary physicist, was the one who actually coined the term cosmic rays. These pioneers were the first to realize that space is a hot environment full of energy we can't see. In Interstellar, Christopher Nolan and his science advisor Kip Thorne had to be very careful about the design of the Endurance. If you look at the ship, it's not just built for aesthetics, it's built to survive. One of the biggest risks for a mission to Saturn is the long-term exposure to GCRs. In the movie, the crew spends years in cryosleep. NASA is currently studying how radiation affects the body during long-term spaceflight, and it's not pretty. It can cause everything from cosmic cataracts in the eyes to DNA damage that leads to cancer. When Cooper and Brand are in the Ranger or the Lander, they are essentially in a metal box. To make Interstellar realistic, the ships would have had to include hydrogen-rich shielding, like polyethylene, to protect the crew. The blight on Earth was a biological disaster, but for the astronauts, the real blight was the constant bombardment of particles trying to tear their cells apart. You don't have to be an astronaut to feel the effects of cosmic radiation. If you've ever taken a long-haul flight from New York to London, you've received a dose of radiation equivalent to a chest X-ray. Because the atmosphere is thinner at 35,000 feet, pilots and flight attendants are actually classified as radiation workers by some health organizations. In fact, airline crews often receive more annual radiation than workers in nuclear power plants. This is why modern aircraft design is so focused on safety. Engineers have to account for single-event upsets, SEUs. This is when a single cosmic ray hits a microchip in the plane's computer and flips a 0 to a 1, causing a glitch. It sounds like science fiction, but it's a real thing that engineers deal with every day to keep us safe in the sky. In pop culture, cosmic radiation is often treated like a superpower-giving serum. The most famous example is the Fantastic Four. Stan Lee and Jack Kirby wrote an origin story where cosmic rays hit a spaceship and gave the crew powers like invisibility and super strength. In reality, if Reed Richards and Ben Grimm were hit by that level of radiation, they wouldn't become superheroes. They'd be in very bad shape. Contemporary shows like The Expanse or For All Mankind handle this much more realistically. They show the storm shelters inside ships where crews have to hide during solar flares. It's a reminder that space is a hostile work environment. In music, David Bowie's Starman and Space Oddity capture that sense of isolation. When Major Tom is floating in his tin can, he's not just lonely, he's being bathed in the ancient light of dead stars. Even Joni Mitchell's iconic line, "We are stardust," takes on a darker meaning when you realize that the same stars that created us are also trying to undo our DNA. Right now, in 2026, the biggest challenge for NASA's Artemis program and SpaceX's Starship mission to Mars is radiation. A trip to Mars takes about 6 to 9 months, During that time, an astronaut would be exposed to more radiation than they would in an entire career on the International Space Station. Scientists are researching active shielding using magnetic fields, like a mini-Earth shield, and passive shielding using water or even lunar soil called regolith. Some researchers are even looking at biotechnology. Could we find a way to make human cells more resilient to radiation? It sounds like something out of a Nolan script, but it's the cutting edge of modern science. It's easy to get scared when you think about invisible particles zipping through your body. But there's a beautiful side to this, too. In Interstellar, the message is that we have to be explorers, not caretakers. But to be an explorer, you have to understand the environment you're exploring. We've spent the last 100 years learning the language of the stars, learning about the radiation they emit so we can build better ships, better planes, and a better future. And it brings us back to that one core idea: love. Love for our families is what makes us build those shields. Love for our MRFs is what makes scientists spend their whole lives in labs trying to figure out how to protect the next generation of explorers. Earth's atmosphere is a physical shield, but our care for one another is our emotional shield. We look up at the stars, and even though we know they're dangerous, we keep going. Because, as Cooper said, we've always defined ourselves by the ability to overcome the impossible. If you've watched Interstellar as many times as I have, you probably remember the climax of the film. Cooper is floating inside the Tesseract, that mind-bending five-dimensional closet behind Murph's bookshelf. He's trying to send her the quantum data from the heart of the black hole, Gargantua. Why? Because without that data, humanity couldn't solve the equation to harness gravity and leave Earth. But here's the thing. You don't need to fall into a black hole to find quantum data. It's actually happening right now inside your own body, in the screen you're looking at, and in the very air you breathe. Now we're peeling back the layers of reality to talk about the structure of matter and its interactions. We're going to see how chemistry and physics aren't just about mixing liquids in beakers. They are fundamentally quantum, and they govern everything from the minerals in the ground to the love in your heart. In the movie, Cooper tells Murph, "Once you're a parent, you're the ghost of your children's future." In physics, atoms are the ghosts of our reality. Everything you see, your cat, your coffee, the stars, is built from these tiny building blocks. But atoms aren't like little billiard balls. They are weird. They are mostly empty space, held together by invisible forces. The way these atoms talk to each other, bond, and react is what creates the world. If gravity is the macro force that moves planets, then the quantum interactions are the micro forces that make life possible. Without the specific way atoms bond, we'd just be a cloud of loose particles floating in the void. To understand how we figured this out, we have to look at the early 20th century. This was the golden age of physics, and the lineup was like the Avengers. Niels Bohr. He gave us the solar system model of the atom in 1913. Even though we know now it's more complex, he was the first to realize that electrons live in specific energy levels. Werner Heisenberg. He introduced the uncertainty principle. He realized that at the quantum level, you can't know exactly where a particle is and where it's going at the same time. This is exactly why the Tesseract in Interstellar looks so chaotic. It's a visual representation of all those possibilities existing at once. Wolfgang Pauli, he gave us the exclusion principle. This is the reason you don't fall through your chair right now. Electrons are picky. They won't share the same state, which gives matter its solid feel. Richard Feynman. Later on, Feynman helped us understand how light and matter interact. He famously said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." These scientists were the Coopers of their time, staring into the unknown and trying to write down the rules of a world they couldn't see. Why does hydrogen bond with oxygen to make water? In high school, we're taught it's about sharing electrons, but the reality is way cooler. It's a quantum dance. Chemistry is basically just applied quantum physics. When atoms get close, their probability clouds, where the electrons are likely to be, begin to overlap. They find a state of harmony where they are more stable together than apart. This happens in mineral formation. The crystals and rocks of the Earth are formed by specific quantum geometric patterns. Biological processes. This is the mind-blowing part. Quantum biology is a real thing. Studies suggest that things like photosynthesis, how plants turn light into food, and even how birds navigate using the Earth's magnetic field rely on quantum effects like coherence and entanglement. Your very existence is a quantum miracle. You might wonder, what does quantum physics have to do with climate change? Everything. The greenhouse effect happens because of how specific molecules like CO2 and methane interact with infrared radiation, heat. At a quantum level, these molecules have specific vibrational modes. When a photon of heat hits a CO2 molecule, if the energy matches the molecule's quantum gap, the molecule absorbs it, vibrates, and then spits that heat back toward Earth. If we didn't understand the quantum structure of matter, we wouldn't be able to model climate change or find the solutions to stop it. Just like the blight in Interstellar required a global scientific effort to understand, our current climate crisis requires us to master the quantum data of our own atmosphere. Naturally, Hollywood loves this stuff. The MCU, Ant-Man and the Wasp, they talk about the quantum realm as a place where the laws of physics break down. While it's very sci-fi, the idea that the microworld is a different dimension of experience isn't entirely wrong. Dark. Netflix. This show dives deep into the bootstrap paradox and quantum entanglement, much like Interstellar does with the ghost in the library. Music. Have you ever noticed how lo-fi or ambient music feels atomic? Artists like Brian Eno or Aphex Twin create soundscapes that feel like they are exploring the spaces between atoms. There's a quantum feel to electronic music. It's built on the very on-off, 0 and 1 logic that quantum mechanics eventually gave us through the invention of the transistor. Right now, in 2026, we are in the middle of a quantum revolution. Quantum computing. Companies like Google and IBM are building computers that use qubits. Unlike normal computers that use zeros and ones, these use superposition, being both at once. These computers will help us simulate new medicines and materials that are literally impossible to design today. The singularity, scientists at the LHC, Large Hadron Collider, are still searching for the graviton, the particle that would finally link gravity, the big stuff, with quantum mechanics, the small stuff. This is exactly the equation that Murph was trying to solve in the movie. It's easy to feel small when you realize you're made of billions of vibrating quantum particles. But remember what Amelia Brand said, "Love is the one thing we're capable of perceiving that transcends dimensions of time and space." In physics, quantum entanglement is when two particles become so linked that what happens to one instantly affects the other, no matter how far apart they are. Einstein called it spooky action at a distance. Isn't that just a scientific way of describing love? Whether it's atoms bonding to form a mineral or humans bonding to form a family, the universe is built on interaction. We are not isolated points. We are part of a massive, beautiful, and complex web of connections. We are the quantum data that makes the universe meaningful. In Christopher Nolan's Interstellar, the Earth is slowly gasping its last breath. The blight is eating the crops, and the dust is taking over. But have you ever noticed that while the Earth is dying, the sun is still up there, shining just as bright as ever? It's a bit of a cosmic irony. The very thing that gives us life, the sun, is also the engine behind the climate and weather that are turning against humanity in the movie. Now we're talking about solar radiation. But we aren't just talking about a big light bulb in the sky. We're going into the heart of the sun to see the quantum fusion that powers it, how that energy travels to us as light and heat, and why the way our atmosphere breathes in those photons is the only reason we are here to talk about it. In the movie, Cooper and the crew are looking for a new home because Earth's engine is failing. But the sun, its engine has been running for 4.6 billion years. This engine is powered by nuclear fusion. Inside the core of the sun, the pressure and heat are so intense that hydrogen atoms are crushed together to form helium. This process releases a staggering amount of energy. But here's the mind-blowing part. According to classical physics, the sun shouldn't be hot enough to do this. The hydrogen atoms have a positive charge, and they should repel each other like the wrong ends of two magnets. So how does the sun do it? It uses a cheat code called quantum tunneling. Basically, at a subatomic level, there is a tiny, tiny chance that a particle can just teleport through a barrier it shouldn't be able to cross. Because there are so many atoms in the sun, this impossible event happens billions of times a second. The sun literally shines because of quantum teleportation. For most of human history, we had no idea how the sun worked. Some people thought it was a giant ball of coal, which would have burned out in a few thousand years. It wasn't until Hans Bethe came along in 1939. Bethe was a German-American physicist who figured out the proton-proton chain, the specific series of reactions that allow the sun to turn mass into energy. He won the Nobel Prize in 1967 for this. Think of Hans Bethe as the Romilly of solar science. While others were looking at the surface, he was doing the deep, quiet math to understand the fundamental forces keeping us alive. Later, scientists like Cecilia Payne-Gaposchkin proved that the sun was mostly made of hydrogen. Before her, everyone thought it was made of the same stuff as Earth. She fundamentally changed our map of the universe, much like Murph changed the map of gravity. When the sun creates energy in its core, it's in the form of photons, particles of light. But a photon's journey is a rough one. It takes about 100,000 years for a photon to bounce its way out of the sun's dense core to the surface. But once it breaks free, it covers the 93 million miles to Earth in just 8 minutes and 20 seconds. When those photons hit our atmosphere, the quantum magic happens again. Our atmosphere isn't just a blanket, it's a filter. Absorption and emission. Molecules like nitrogen, oxygen, and CO2 interact with these photons at a quantum level. Each molecule has specific energy levels. If a photon's energy matches that level, the molecule absorbs it. The sky's color. This is why the sky is blue. The shorter, bluer wavelengths of light are scattered by the molecules in the air, a process called Rayleigh scattering. If the crew of the Endurance looked back at Earth from the blackness of space, that pale blue dot is only blue because of the way quantum particles are dancing in our air. The sun is the ultimate main character in science fiction. Sunshine, 2007. Long before Interstellar, Cillian Murphy starred in this movie about a mission to restart a dying sun. It's a beautiful, terrifying look at the sun's raw power. Spider-Man 2, Doc Ock's famous line, "The power of the sun in the palm of my hand," is a direct reference to trying to create cold fusion on Earth, the holy grail of energy research. Music. You can't talk about the sun without the Beatles' "Here Comes the Sun," a song about hope and the return of light. Or Soundgarden's "Black Hole Sun," which captures that darker, more gargantua-like vibe. The sun represents everything from divine love to inevitable destruction. Right now, in 2026, we are living through some of the most exciting solar research in history, ITER and fusion power. Scientists in France and around the world are trying to build artificial suns on Earth. If we can master nuclear fusion, the same process happening in the sun, we would have clean, limitless energy forever. No more blight, no more resource wars. It would be the real-life version of solving the equation. Solar maximum. We are currently in a period of high solar activity. This means more sunspots, more flares, and more energy hitting our atmosphere. It's a reminder that we live in a dynamic system. The sun isn't just a static object, it's a living, breathing star. In Interstellar, the environment becomes unstable. On our Earth, that stability depends on the balance of radiation. The sun sends shortwave radiation, light, down to us. The Earth absorbs it and tries to send longwave radiation, heat, back out into space. But greenhouse gases, thanks to their quantum structure, trap some of that heat. A little bit of trapping is good. It keeps us warm. Too much trapping and we end up with a climate crisis that could lead us to a Cooper-level desperation. Understanding the quantum interaction between a photon and a CO2 molecule is literally the key to saving our planet. We have to be the scientists who balance the equation before we are forced to be the pioneers who leave. We always end here because it's the truth. Everything is connected. Amelia Brand was right about love transcending dimensions, but you could say the same about the sun's light. The light hitting your skin right now was born in the heart of a star 100,000 years ago. It's a connection to the deep past and a promise for the future. The sun provides the energy for plants to grow through photosynthesis, another quantum process. Those plants provide the oxygen we breathe and the food we eat. Every heartbeat, every thought, and every feeling of love you've ever had is, in a way, powered by solar radiation. We are literally children of the sun. So as you drift off to sleep, imagine that golden light. It's not just warmth, it's a quantum bridge. It's a reminder that even in the cold, dark void of space, there is a star burning just for us, keeping the endurance of life going for one more day. Imagine you're on the deck of the Endurance, looking back at Earth as it fades into a tiny blue dot. You'd see the deep blue of the oceans and the swirling white of the clouds, but if you happen to look toward the poles, you'd see something that looks like magic, glowing, dancing ribbons of green, purple, and red light. In Christopher Nolan's Interstellar, we spend a lot of time looking at the unnatural beauty of the cosmos, the golden glow of Gargantua's accretion disk, or the kaleidoscopic colors inside the tesseract. But Earth has its own version of a quantum light show happening right in our atmosphere. Now we're talking about atmospheric phenomena, specifically the local color of auroras. We're going to look at why the sky turns green in Norway, the quantum jumps happening in our oxygen, and how these lights are a bridge between our world and the deep chaotic energy of the sun. An aurora isn't a cloud, and it's not a reflection, it's a collision. It all starts with the sun sneezing, a solar wind of charged particles, electrons and protons, flying toward Earth. When these particles hit our magnetic field, they are funneled toward the north and south poles. As they slam into our upper atmosphere, they crash into atoms of oxygen and nitrogen. Think of it like a cosmic game of billiards. The solar particle hits the atom and gives it a huge burst of energy. The atom gets excited. It jumps to a higher energy level. But atoms don't like being excited for long. They want to go back to their chill state. When they drop back down, they release that extra energy as a photon, a tiny burst of colored light. This is a quantum electronic transition. It's the exact same logic that Cooper uses in the tesseract to communicate with Murph. It's about sending a signal through a specific change in state. If we're talking about the history of the Northern Lights, we have to talk about Norway. Specifically, a scientist named Christian Birkeland. In the late 1800s and early 1900s, while most people still thought auroras were reflections of sunlight off ice or even ghosts, Birkeland had a wild idea. He thought they were caused by particles from the sun. To prove it, he built the Terrella, a magnetized metal sphere inside a vacuum chamber that represented the Earth. He fired electrons at it, and lo and behold, he created mini auroras around the poles of his little metal Earth. Birkeland was the Cooper of his time. He went against the mainstream science of his day to prove a connection between the Earth and the stars. Today, his face is on the Norwegian 200 kroner note, and he's the reason why Norway is the capital of aurora research. Why isn't the aurora just white? This is where the chemistry gets beautiful. The color depends on which atom is being hit and how high up in the atmosphere it is. The ghostly green. This is the most famous color, the one you see in those stunning photos from Tromsø or the Lofoten Islands in Norway. It's caused by oxygen atoms about 60 to 150 miles up. It's a very specific quantum transition that gives off that neon green glow. The high-altitude red. If the solar particles hit oxygen even higher up, above 150 miles, the quantum jump is different, resulting in a rare deep red aurora. In interstellar terms, this is like the deep space version of the light. The purple and blue borders, these are caused by nitrogen. Nitrogen is harder to excite than oxygen, so it usually only glows during intense solar storms, creating those beautiful purple edges at the bottom of the aurora curtains. Christopher Nolan is obsessed with visual verisimilitude, making things look scientifically real. When they designed the Tesseract, they used a lot of vertical lines and shifting colors to represent fifth-dimensional space. If you look at an aurora, it's basically a natural tesseract. It's a three-dimensional representation of a four-dimensional event, the interaction of time-traveling solar particles with our magnetic field. When you stand under the lights in a place like Iceland or Alaska, you feel like you're looking through a window into another dimension. You're seeing the breath of the sun interacting with the skin of the earth. It's the closest thing we have to a physical wormhole visual in our daily lives. Auroras are everywhere in our stories. The golden compass, his dark materials. In this series, the dust, similar to the data Cooper sends, is visible through the aurora borealis. It's seen as a bridge to other parallel worlds. Disney's Frozen. The opening of the movie features the northern lights as a symbol of the magic of the Scandinavian landscape. Aurora, the artist. The Norwegian singer Aurora creates music that feels like the lights themselves, ethereal, pulsing, and deeply connected to nature. Radiohead. Their song, Subterranean Homesick Alien, mentions upturned smiles watching the lights. There's a persistent vibe in indie and alternative music that the aurora is a sign that we are not alone. Right now, in 2026, we are coming off a solar maximum. This is a peak in the sun's 11-year cycle. Because the sun has been so active, people have been seeing the aurora borealis much further south than usual, places like England, Germany, and even parts of the United States like Pennsylvania and Oregon. NASA is currently using the Themis mission, a fleet of 5 satellites, to study how these substorms work. They are trying to understand the space weather that creates these lights. Why? Because the same energy that makes the sky pretty can also fry our satellites. We have to understand the quantum dance of the aurora to protect the very technology that allows us to watch Interstellar on our phones. We always wrap up with the heart of the matter. Amelia Brand said love is the one thing that transcends dimensions. When you stand in the cold Norwegian night, looking up at a green ribbon of light dancing across the stars, you feel a profound sense of connection. You're connected to the sun, 93 million miles away. You're connected to the oxygen molecules keeping you alive. And you're connected to every human who has ever looked up at those lights and felt a sense of wonder. The aurora is a reminder that the universe is talking to us. It's sending us data in the form of light. Just like Cooper used the watch to send data to Murph, the sun uses the aurora to tell us about its energy. Our job is to be like Murph, to look up, to pay attention, and to realize that even in the vast cold emptiness of space, there is a beautiful, colorful conversation happening, and we are a part of it. In Christopher Nolan's Interstellar, the Earth is being strangled. It's not a war or a nuclear bomb that's doing it, it's the blight. This mysterious, suffocating organism is consuming the world's crops, starting with wheat, then okra, and eventually leaving only corn. The blight doesn't just eat the food, it breathes nitrogen, depleting the oxygen we need to survive. But why was the blight so terrifying? Because it struck at the very heart of the most important biological process in the history of the universe, photosynthesis. Now we're going to explore the miracle of how plants turn sunlight into life, but we aren't just looking at biology. We're going deeper into the weird, spooky world of quantum coherence. We're going to find out how every leaf on every tree is essentially performing a quantum calculation to survive, and how this original wormhole of energy is what keeps our world from turning into the dusty wasteland of Cooper's farm. Most of us learn the basics in grade school. Plants take in sunlight, water, and CO2 to create oxygen and sugar. It sounds simple, right? Like a solar panel. But if you look closer, photosynthesis is actually incredibly inefficient in terms of how much total sunlight it captures. However, once that light hits a leaf, the way it moves that energy is nearly 100% efficient. Inside a plant cell, there are light harvesting complexes called antennae. When a photon, a particle of light, hits one, it creates an exciton, a little packet of energy. This exciton has to find its way to the reaction center to be turned into chemical energy. If it takes too long, the energy is lost as heat. But the exciton finds the center almost instantly, every single time. How? This is where it gets very interstellar. For a long time, scientists thought the energy just hopped randomly from one molecule to another until it stumbled upon the reaction center, but that's too slow. In the late 2000s, researchers like Graham Fleming and Seth Lloyd discovered something mind-blowing. Plants use quantum coherence. Instead of taking one path at a time, the exciton acts like a wave. It explores every possible path simultaneously. It's like Cooper in the Tesseract, seeing every moment in Murph's life at once. The energy senses the most efficient route to the reaction center and takes it. It's essentially a biological quantum computer. By being in multiple states at once, superposition, the plant ensures that not a single drop of solar energy goes to waste. In the movie, the ghost in Murph's room is actually her father communicating across dimensions. In a way, quantum coherence is the ghost in the machine of life. When Cooper is in the Tesseract, he's navigating a fifth-dimensional space to find the exact moment to send the data. A leaf is doing the exact same thing in a quantum dimension. The blight in the movie was so deadly because it was a biological dead end. It broke the connection between the sun's energy and the Earth's life. Professor Brand's entire goal was to solve gravity to save humanity, but nature already solved quantum mechanics billions of years ago. Every time you breathe, you're breathing the byproduct of a quantum calculation. We don't just live on a planet, we live inside a massive green quantum network. The history of photosynthesis is a long journey of looking closer. Jan Ingenhousz, 1779. He was the first to show that plants need light to purify the air. He was a Dutch physician who figured out the plan A of the Earth, that we are in a symbiotic relationship with the green stuff. Melvin Calvin, 1940s to 50s. He mapped out the Calvin cycle, how CO2 becomes sugar. He used radioactive carbon to trace the path, like a detective. He won the Nobel Prize in 1961. Modern quantum biologists. Today, scientists are using ultra-fast laser spectroscopy to watch these quantum jumps in real time. They are finding that this coherence isn't just a freak accident. It's fundamental to how life survives in a chaotic universe. We are obsessed with the idea of plants as our literal lifelines. The Martian, Mark Watney, Matt Damon, who, fun fact, was also Dr. Mann in Interstellar, survives because he masters botany on a dead planet. He creates his own mini biosphere. It's a tribute to the power of photosynthesis to turn a wasteland into a home. Avatar. James Cameron's Pandora is a world where the plants are literally connected in a neural network, AWA. This isn't far from the truth of how trees communicate through fungal networks on Earth. It's a macro version of the quantum coherence happening in their leaves. Music. Think of the album Plantasia by Mort Garson, 1976, music specifically made for plants to grow to. Or the band Radiohead, who often use organic, glitchy sounds to mimic the bridge between nature and technology. Songs like Lotus Flower or There capture that rhythmic, almost mathematical pulse of the natural world. Right now, we are in a race against our own blight, climate change. Artificial photosynthesis. Scientists are trying to build bionic leaves that can capture CO2 and turn it into fuel or plastic more efficiently than real plants. If we can master the quantum shortcut that plants use, we could create a carbon-negative economy. Vertical farming. We're taking photosynthesis indoors, using specific LED frequencies, mostly blue and red light, to hack the quantum response of plants, growing food in the middle of cities without needing vast amounts of land. It's the first step toward the NASA-style hydroponics we see in the Endurance. We always end on the same note because it's the most important one. Amelia Brand said, Love is the one thing we're capable of perceiving that transcends dimensions of time and space. If you think about it, photosynthesis is a form of cosmic love. It's the sun, 93 million miles away, sending a gift of energy to the Earth. And the plants, through their quantum shortcuts, make sure that gift is received and shared with every living thing. Just as the data Cooper sent through the watch was the key to Murph's survival, the data sent by the sun through photons is the key to ours. We are connected to the stars not just by gravity, but by the very chemical bonds in our bodies. So as you go to sleep tonight, think about the oxygen in your room. It was made by a quantum ghost in a leaf. It's a reminder that we are part of a system that is far more intelligent, far more connected, and far more beautiful than we often realize. We aren't just observers in the universe, we are the result of its most brilliant calculations.